Let us solve a problem where air undergoes a constant volume process. It could be a rigid tank, or in this case, a piston cylinder device where the stops prevents the piston from moving, and we have air inside. Notice, let's look at the beginning and the final state of this. In this case, the beginning state is given here. We'll call it state 1. And instead of a paddle wheel doing work, we'll say heat is transferred. 800 kilojoules of heat is transferred to the air. So let's simplify the problem. We'd like to know the final pressure, find final temperature, and final pressure. How about that? And we'll use the PG model. Every time we work with a gas, we'll use the PG model for simplification. First thing first, let's do a TS diagram to make sure we understand the process, how it will look. Recall, a constant volume line is steeper than a constant pressure line, looks something like this. So if this is state 1, this could be state 2 in a TS diagram, and the area underneath is proportional to the heat transfer, right? Let's call it Q in is proportional to this area. Okay, so let's begin by evaluating the beginning and final state first. So what is known is that for the beginning state, let's call it state 1, we have been given pressure, temperature, 25 degrees Celsius. Let's convert it to Kelvin. And I think the volume is supplied. So we know we are going to need the mass. So quickly let's apply the ideal gas equation of state, PV equals RT. And recall, for air we are going to use R equal 0.287 kilojoule kg Kelvin. As a result, we can figure out specific volume RT over P, substituting the values. It turns out to be 0.475. And we know specific volume and the total volume are related. Specific volume is what? Total volume by mass. So therefore, mass equals it turns out to be about 4.207. So we found the mass of the air that is trapped. So let's quickly verify, because a mistake is always possible. So we go to TESTcalc, and we follow the system analysis, a closed system in this case, and it's going through an unsteady closed process, and we have a generic uniform systems. The specific branch we'll only use for special situation, like when we solve IC engine problems, combustion, etc. Otherwise, you'll follow the generic branch, and it's a uniform system. Uniform system means a single state describes the beginning state or the final state. And finally, we click PG model to launch and select the PG TESTcalc tab to launch the TESTcalc. The first thing is to select the gas, which is air, and 180 kPa is given to us. Temperature is given to be 25 Celsius, and volume is given to be 2 meter cube, and we obtain the mass to be 4.2. That's exactly what we got. Okay, so let's proceed. Go back to here, and this time, so we are done with state 1. Let's go find state 2. So what do we know about state 2? Of course, specific volume doesn't change because the mass is the same, volume is the same. The specific volume is still 0.4 0.475. But we need one more property, one more thermodynamic property. Recall P, T, V, U, H, and S are thermodynamic properties. So we need two of those to find rest of the properties. So we want to find pressure and temperature. We only know specific volume. So to find another property, we realize nothing else is given to us except the heat transfer is given to us. So if we apply the energy equation for the heating process, the energy equation, if you recall, delta E equal Q minus W external. If we neglect KE and PE, then it becomes delta U equals Q. And there is no work in that case. There is no shaft, there is no electricity, there is no boundary work because the system volume doesn't change. So WB equals 0, W shaft equals 0, W electricity equals 0. Therefore, W external equals 0. And the Q is supplied, so M delta U formula is what? M CV delta T equal Q. If we substitute the values, M is 4.21. CV for air is 0.718. Again, the value would be usually given, or you can go to the PG model, the PG table, and figure and obtain the value directly. So this is a material property, it will be given to you. And delta T equals T2 minus T1, obviously. And Q is given. Q is 800. And T1 is given 298. So we can solve this problem, obtaining T2 equals 504 Kelvin. So how do we find pressure? Of course, if we just use ideal gas equation, PV equals RT, that will give us the pressure. Pressure will be RT over V. Temperature is 504. And specific volume is same as state 1. And that gives us the pressure of 340 kPa. So it's really simple. And so an energy analysis produces our state 2. Let's go and verify. So what we know about state 2? Well, here we know that mass is the same. We know the volume is the same. So just this to see the TESTcalc understand that specific volume is the same. You cannot enter specific volume if you already enter mass and volume, because it can be obtained from mass and volume. So the other thing is that here we could find an equation for U2 and substitute. Alternatively, we could go to the process panel and say for state 1 we have for B state we have state 1, and for the final state we have state 2, and Q is given to us. 800 kilojoule of heat is added. So if we solve, and there is no other kind of work. WO means external work, boundary work. WO means shaft and electrical work. That is also 0. So once we enter that, and if we evaluate, we solve the energy equation, you will notice if you go back to the state panel, E2 has been evaluated and substituted here. That's why it is a gray background. So we can just hit calculate, and therefore the temperature is evaluated. Alternatively, we could enter an equation here because we have already shown that delta U equals Q. So we could just write an equation here for E2. So either way, so we show that the temperature is 290. The pressure is 340 kPa, and the temperature is oh, this is Celsius, so in Kelvin it is 563 kPa, 563 Kelvin. So we have solved this constant volume process. In this constant volume process, therefore, the energy equation essentially is very simple. That's the only thing this is the biggest takeaway, delta U equals Q minus W external. For any constant volume process goes to 0. There's no external work. So therefore, for a perfect gas, the equation is really simple. Q equals mCv delta T. So the heat transfer in a constant volume process is given by this equation. So very handy equation for a constant volume process. We are going to use it over and over again when we analyze an internal combustion engine. Well, now suppose we want to make the process a constant pressure process. So the state 1 is the same as the original problem, but now the piston is free to move, so therefore pressure remains constant. So let's assume that heat in is the same amount, 800 kilojoule, and again we want to find the final, let's say final volume and final temperature. Of course, the final pressure will be the same because pressure doesn't change. So we want to evaluate state, let's call it state 3. So this time pressure remains constant. How does the process look? In the TS diagram, recall, it is similar to constant volume line, except the constant pressure line is a little bit less steep, and the area underneath is proportional to the heat that is added. So what do you know about this state? Pressure doesn't change, so 180 kPa. Of course, we have already evaluated mass. Mass doesn't change. I think it was 4.21 kg of air. And we know 800 kilojoules of heat is added. The energy equation, if you recall, for the closed process, if, of course, it will become almost mechanical to write E equal U, because we'll assume there is no change in KE and PE. So we'll neglect KE and PE, changes in them, therefore E equals U. But this equation, notice we cannot find WB here because we don't know the final volume. We know the pressure remains constant, so it's easy to find the boundary work. But we know for constant pressure process, we showed that the equation can be simplified, and it turns out to be delta H equal Q. When you substitute, if you recall from our analysis before, pressure remains constant, so it's volume, change in volume times pressure, and when U and PV are combined, we get enthalpy. So the equation becomes very simple. Q equals M H3 minus H1. Sorry, state 3 is my final state here. So therefore, if we want, we can write H3 is obviously Q over M plus H1. That's what we can use in the TESTcalc. But to find the temperature, this is simply Q. To solve it manually, Q equals M H3 minus H1. 800 is my Q. M is 4.21, and it's Cp T3 minus T1 instead of Cv. 4.21, 1.005. So if we solve this, we can find T3. We can find. We can also find volume using the ideal gas equation. So this turns out to be 488 Kelvin. And if we want to find the volume, we can just use PV equals RT. Because now we know temperature, we know, of course, we know the R and we know the pressure. This will give us specific volume of 0.777 and a total volume of, because we know the mass already, mass times specific volume equals 3.27 meter cube. Now that we know the final volume, we can find boundary work. If the question is find boundary work, it will be what? The pressure times V3 minus V1, 180 kPa, 3.27 minus 2. We can calculate that in a second. But notice that the final temperature that we get, 488 Kelvin, in a constant pressure process is slightly lower than the final temperature that we got. What was T2 in this case? We got a temperature of 504 Kelvin. So can you see that the temperature when we used a constant volume process is higher than the temperature when we have a constant pressure process? And it becomes clear why, because look, the same amount of heat, previously it went into raising the temperature, the internal energy of the system, and now part of it also goes into doing the boundary work. So the temperature rise is not so much as before. Okay, let's make sure we verify this result. So we go back and try to find state 3, where state 3 is pressure doesn't change, so pressure is the same, mass doesn't change, and we know enthalpy we can relate equals H1 to H1 plus 800, that was the heat transfer, divided by mass, which is M1 I can put, and that gives us the temperature is verified. We go to the process panel, and process B, remember process A was our state 1 to state 2 constant volume process. Now it goes from state 1 to state 3. Notice the boundary work is immediately calculated because the TESTcalc recognizes that the pressure remains constant. Other work means shaft and electrical work is 0, so we put that in, and Q is, actually we can now calculate Q because we already put it in our state is completely known, so 800 kilojoules. Boundary work is found, 228, so I bet this will be 228 if we calculate this. So therefore, we just analyzed a constant pressure process and a constant volume process. Go over this problem so that you thoroughly understand that, because we are going to use that in the analysis of internal combustion engine quite a bit.